quantum mechanics. Yeah, there's really no question. It's the most powerful, most successful scientific theory we've ever come up with. It's behind pretty much every bit of microelectronics you use every day.
Absolutely. Your phone, satellites, lasers,
Mm.
all quantum.
And yet, even the physicists who build this stuff, who use it constantly, they often describe it as, well, fundamentally mad. It just seems crazy.
Right. It works perfectly, the predictions are spot on, but it leaves you feeling like you're chasing ghosts. Particles that are somehow waves too, and of course that cat.
Ah, yes, the alive and dead cat. It creates this real intellectual tension, doesn't it?
It really does. The math is, well, flawless. We can calculate outcomes with incredible precision. But then you ask that crucial scientific question, okay, but what's really going on underneath? What reality makes this math work?
And the universe just kind of shrugs.
Pretty much. Or it gives you answers that seem to defy common sense.
So the sources we looked into for you really highlight this. They show that this mystery, this sense of madness, it only really starts to make sense, or at least become manageable, when you face a fundamental philosophical choice.
Exactly. Do you take the mathematical description, the wave function and all that, literally, as describing real physical things out there? That's realism.
Or do you say, look, the math is just a tool, a really, really good tool for predicting what we'll observe, but maybe it doesn't actually represent reality itself. And that's anti-realism.
That's the fork in the road.
Okay, let's unpack this. Because if you choose realism, if you say the math is reality, then suddenly our basic intuitions about how the world works seem completely wrong.
Right. And you start asking, what good is a scientific theory if you can't point to its core elements and ask, but how does nature actually do that?
That's the heart of it, isn't it? That refusal by some physicists to just accept the predictions without demanding a mechanism. That's the quantum interpretation battleground.
Precisely. So to really get into this fight, we need a quick refresher on the quantum rules of engagement. First big one. The quantum world is lumpy, discrete.
Not smooth and continuous like we experience things mostly.
Exactly. Everything comes in chunks. And the size of these fundamental chunks, the smallest bit of energy or action, is set by Planck's constant, dollars in error. If you see an dollar in an equation, that's the telltale sign you're dealing with quantum stuff.
Okay, lumpiness. And that lumpiness leads straight to the weirdest part for me, wave-particle duality.
Light, which we all learn about as waves, sometimes acts like a stream of tiny particles, photons. And even weirder, things we think of as particles, like electrons, can act like spread-out waves.
Both things at once.
Depending on how you measure them.
Which brings us to the absolute classic, the two-slit experiment.
The cornerstone. Yeah. You fire electrons, just one after the other, at a wall with two narrow slits in it.
Okay, like tiny bullets. You expect two lines on the screen behind the wall where they went through.
Right. But that's not what you get. You get an interference pattern, stripes of many electrons hitting, and stripes of none hitting. That pattern is the dead giveaway of wave behavior.
So the single electron somehow must be going through both slits simultaneously like a wave and interfering with itself.
That's what the pattern implies. It's delocalized. But here's the kicker.
There's always a kicker with quantum mechanics.
Always. If you put a detector at the slips to see which slit the electron actually goes through, poof, the interference pattern vanishes.
And you get the two lines, like the bullets.
Exactly. The very act of measuring, of observing which path, forces it to behave like a particle. It snaps out of its wave-like state.
Okay, mind-bending. And the math describes this spread-out wave thing.
Yes, that's the wave function, usually written as a Furfunkers. But here's another rule. The wave function only gives you probabilities. That's the Bohr rule.
Probabilities, like the chance of finding the electron here versus there.
Precisely. It tells you the odds, what might happen when you measure, but never definitively what will happen.
Now, we need to be clear. This isn't like flipping a coin, right? With a coin, it is heads or tails while it's spinning. We just don't know which one until it lands. Our ignorance causes the probability.
That's the crucial difference. In quantum mechanics, the probability seems fundamental. The electron doesn't have a definite position or definite spin before you measure it. It exists in a fuzzy state of multiple possibilities at once, a superposition.
Which is why Einstein hated it. God does not play dice. He wanted certainty underneath.
You really did. And this leads to the final massive headache, the collapse of the wave function.
Okay.
The main equation of quantum mechanics, the Schrödinger equation, says the wave function should evolve smoothly, predictably, continuously over time.
Like a wave rippling out.
Exactly. But when we make a measurement, the wave function seems to instantaneously jump or collapse from that spread out state of many possibilities down to a single definite outcome.
The electron is suddenly here, not just potentially here or there.
Right. And the huge problem, the one that fuels all these interpretations, is that there's nothing in the standard Schrödinger equation itself that explains how or why this collapse happens. It's like an extra rule tacked on without mathematical justification from the core dynamics.
So the math describes the before superposition and predicts the after probabilities of outcomes, but the during the jump itself is a mystery.
That's the measurement problem in a nutshell.
Okay, so facing this weirdness, one path is anti-realism. If we imagine science as this ship of science sailing between, say, metaphysical reality, our deep intuitions and abstract ideas, and empirical reality, the hard data we observe.
Then the anti-realists basically say, let's hug the coast of empirical reality. Let's stick to what we can measure and predict.
Don't worry too much about the metaphysical deep sea.
Pretty much. And the classic version of this is the Copenhagen interpretation, developed mainly by Niels Bohr and Werner Heisenberg back in the early days.
This was the standard view for a long, long time, right?
Oh yeah, absolutely dominant. And it's anti-realist because it specifically tells you not to take the wave function too literally as a real physical ways out there in the world.
So how did Bohr handle the wave-particle paradox, if it's not a real wave or a real particle?
Bohr's idea was complementarity. He argued that wave and particle are like complementary descriptions. You need both to fully characterize the quantum system, but you can only ever see one aspect at a time, depending on the kind of experiment you do.
Like two sides of a coin you can never see simultaneously.
Kind of. He saw them as shadows cast by the quantum reality onto our classical measuring instruments. Because we're stuck using classical language and classical devices to poke the quantum world, we're fundamentally limited in what we can say about the underlying reality in itself.
So Copenhagen basically says, the math works incredibly well for predicting the shadows, so just use the math and, well...
Shut up and calculate.
Excellent.
That became the unofficial motto. Don't ask unanswerable questions about what the wave function is. QM is complete as a predictive tool, so stop looking for some deeper mechanism.
Okay. But anti-realism didn't stop there, did it? There are more modern takes.
Right. Some newer views move away from Bohr's focus on the classical apparatus and lean heavily into information. Take Carlo Rovelli's relational quantum mechanics.
Or QM, what's the idea there?
Rovelli argues that a quantum state doesn't exist in any absolute sense. It only exists relative to something else, an observer, another system, a measuring device. The wave function isn't the system itself, it's just a mathematical way of encoding our information or knowledge about the system based on its interactions.
So the state is defined by the relationship between systems, no observer-independent reality.
Essentially, yes. It avoids the collapse by saying that state description was always relative to a specific observer or interaction context in the first place.
That seems less philosophically loaded, maybe. But then there's quantum Bayesianism or QBism. That sounds like it goes even further.
QBism takes the subjectivity to the max. It says those quantum probabilities aren't objective features of the world at all, they're Bayesian probabilities. Meaning they reflect an individual agent's, like an experimenter's, personal, subjective degree of belief about the outcomes of their actions on the world based on their past experience.
Whoa! So quantum mechanics isn't even a theory about the world, it's a theory about how I should update my beliefs.
In the QBist view, yes. It's a tool for navigating and making sense of my experience. It strongly implies that my reality, or at least my quantum description of it, might be fundamentally different from yours because our experiences and beliefs differ.
Okay, that feels pretty radical. Giving up on objective reality seems like a big step for science.
It's definitely one of the most debated aspects of QBism. So if the anti-realists decided to focus on calculation and information, the realists couldn't let go of that fundamental question, what's really going on? People like Einstein, Schrödinger.
The old guard in some ways.
Right. They insisted that science has to aim for a description of objective reality. They felt QM, with its probabilities and observer dependence, must be incomplete.
Like there's a deeper layer we just haven't found yet. Hidden variables.
Exactly. They suspected the probabilities were like, in classical statistical mechanics, just a sign of our ignorance about some underlying deterministic hidden reality. If we knew the hidden details, the probabilities would disappear.
And Einstein came up with a way to challenge this head-on, didn't he? The EPR paradox?
Yes, in 1935, with Podolsky and Rosen, it's a brilliant thought experiment. Imagine you have two quantum particles, A and B, that interact in a specific way so their properties are linked, entangled. For example, their spins must be opposite.
Okay, like one spins up and the other must spin down.
Precisely. Now let these particles fly far apart, light years even.
Okay?
Now if you measure the spin of particle A and
Well,
find it's up,
then you instantly know with 100% certainty that particle B, way over there, must be down, even though you haven't touched B or interacted with it in any way since they separated.
that's the core issue. For Einstein, this instantaneous knowledge across a vast distance looked like information traveling faster than light, which special relativity forbids. He called it spukhafte Fernwirkung, spooky action at a distance.
And he argued that the only way B could know to be down, the instant A was measured up without spooky action, was if its state down was already predetermined from the moment they separated. There had to be some hidden instruction, some local hidden variable.
Correct. He insisted that any acceptable reality must be local, no faster than light influences.
But this was just a thought experiment for decades. Then came John Bell.
Ah, John Bell, the physicist who figured out how to turn Einstein's philosophical objection into a testable scientific question. He used a great analogy, Bertelsmann's socks.
Right, the professor who supposedly always wore mismatched socks.
Yeah. If you see his left sock is pink, you instantly know his right sock isn't pink. But there's nothing spooky there. You know it because you know his habit, the hidden variable, was his choice when he got dressed. The correlation was predetermined locally.
Einstein hoped quantum entanglement worked like that.
He did. But Bell, in 1964, did the hard math. He derived a mathematical inequality, Bell's inequality, that any theory based on local hidden variables, any theory that assumes both locality, no spooky action, and realism, properties exist before measurement, must obey.
Okay, so a concrete prediction based on Einstein's intuition.
Exactly. And crucially, standard quantum mechanics predicted results that would violate Bell's inequality under certain experimental setups.
So we have a clear fork. If Einstein's local realism holds, Bell's inequality is respected. If quantum mechanics is correct, it's violated. You just had to do the experiment.
And they did, starting famously with Alain Aspect in France in 1982, and then many, many times since, with increasing precision, closing potential loopholes.
And the verdict.
Overwhelmingly, consistently, the experiments violate Bell's inequality. They match the predictions of quantum mechanics, not local realism.
Wow. So wait, let's talk about those loophole tests. The source mentioned one in 2018 using light from quasars, billions of light years away.
Yes, that was incredible. One potential loophole was the freedom of choice loophole. Maybe the choice of what measurement to make on particle A wasn't truly random. Maybe it was somehow correlated with the state of particle B through some hidden communication faster than light, or some common cause in their shared past.
So they used light from incredibly distant ancient quasars to randomly determine the measurement settings.
Exactly. The idea was that the decision about which measurement setting to use was made by photons that had been traveling for billions of years, long before the entangled particles were even created. There's no conceivable way the particles could have known or coordinated based on that ancient random choice via local means.
And even then,
Bell's inequality was violated. Quantum mechanics held up.
so a conclusion seems inescapable.
It really is, scientifically speaking. Local realism, the intuitive picture Einstein clung to, that reality exists independently out there, and influences don't travel faster than light, that picture is dead.
One of those assumptions has to go.
At least one. Any interpretation that wants to maintain realism, that properties are real before measurement, must embrace non-locality. Spooky action is real. Or give up some other fundamental principle, perhaps even causality under certain definitions.
Okay, here's where it gets really interesting, as the source puts it. If you're a realist, you've just seen your most comfortable assumption locality shot down by experiment. You refuse to just shut up and calculate. What do you do now? You have to pick your poison, essentially.
Right. You have to choose which counterintuitive feature you're willing to accept to make the theory complete or real. One path, which actually predates Bell but gained new relevance after, is the de Broglie-Bohm pilot wave theory.
Bohmian mechanics, how does that work?
It's fully deterministic. It says particles, like electrons, always have definite positions. There are no probabilities at the fundamental level, but their motion is guided by a real physical wave, the wave function, now seen as a pilot wave or quantum potential.
So the particle is real, the wave is real, and the wave tells the particle where to go.
Basically, yes. It perfectly reproduces all the predictions of standard quantum mechanics, including the interference patterns and Bell violations. But the cost is embracing non-locality explicitly,
Meaning?
meaning the pilot wave acts instantaneously across any distance. Measuring particle A instantly changes the pilot wave everywhere, which instantly influences particle B's trajectory no matter how far away. Spooky action is built right into the dynamics.
So they bite the non-local bullet to save determinism and realism about particle positions.
They do. Proponents argue this non-locality can't be used for faster-than-light signaling, so it doesn't violate relativity in that practical sense, but it's still deeply counterintuitive.
Okay, what's another realist option? Tackling the collapse.
Exactly. Instead of just accepting the collapse postulate, try to explain it physically. Add something to the Schrödinger equation to make the collapse happen automatically under certain conditions. These are physical collapse mechanisms.
And a big part of that discussion involves decoherence, right?
Yes, decoherence is a crucial piece of the puzzle, though not a full solution itself. It's a well-understood physical process.
Explain that again. How does it work?
Any quantum system, especially a large one, is never truly isolated. It's constantly interacting, bumping into air molecules, photons, etc., getting entangled with its environment.
The warm, wet, noisy, real world.
Right. These countless tiny interactions very rapidly scramble the delicate phase relationships needed for quantum superposition to be observable on a large scale. The waviness, the interference terms, effectively get washed out into the environment almost instantly for macroscopic things.
So that's why we don't see cats that are both alive and dead. Decoherence makes that state decay incredibly fast.
Exactly. It explains why macroscopic objects appear classical. It provides a practical boundary.
But you said it's not a full solution to the measurement problem. Why not?
Because decoherence turns the and, alive and dead, into an or, alive or dead, by suppressing interference. It explains why we don't see the superposition. But it doesn't explain how or why one specific outcome, alive for instance, is randomly selected from the remaining possibilities when an actual measurement occurs. The randomness is still there.
Ah, okay. It explains the transition towards classical outcomes, but not the final definite choice.
Precisely. So collapse models like GRW, Urardi-Rimini-Weber, or Penrose's ideas try to add a physical mechanism maybe related to gravity or just spontaneous random hits that forces the wave function to collapse into one specific state, solving that final step.
Does this connect to consciousness? I remember reading about Wigner's friend.
Ah, yes. That's a more philosophical and highly controversial extension. Some, like Eugene Wigner, wondered if the final collapse only happens when the result enters the awareness of a conscious observer. This leads to paradoxes like Wigner's friend, where one observer is inside a lab seeing an outcome, but an observer outside doesn't know the result yet. Is the state collapsed for one but not the other? It gets very tricky and isn't a mainstream physical view, but it highlights the depth of the problem.
All right, let's shift gears to maybe the most mind-bending realist proposal of all. The one that tries to save the math, preserve realism, but does something truly radical. It just gets rid of the collapse postulate altogether.
That's the Many-Worlds interpretation, MWI, first proposed by Hugh Everett III in his 1957 PhD thesis.
Everett's idea, what's the core concept?
It's incredibly simple in a way, Everett said. What if we just assume the Schrödinger equation is always correct for everything, including observers and measuring devices? What if the wave function never actually collapses?
But wait, if it never collapses, how do we explain our experience? I mean, when I measure an electron spin, I definitely get one answer up or down, not both.
This is where it gets wild.
Yeah.
Everett's answer is that when a measurement-like interaction occurs, one that could have multiple outcomes, the entire universe, including the observer, the apparatus, everything entangled with it, literally splits or branches.
Splits into what?
Into multiple parallel coexisting universes. In one branch, the electron was measured up, and the version of you in that branch saw up. In another completely separate, non-interacting branch, the electron was measured down, and the version of you in that branch saw down.
So every quantum choice creates new universes.
Every quantum interaction with multiple potential outcomes leads to branching, yes.
Sure.
All possible outcomes actually happen, just in different, mutually inaccessible worlds.
Okay. I remember the description. Cheap on assumptions, but expensive on universes.
Breathtakingly expensive. Bryce DeWitt, who popularized Everett's work, estimated the number of parallel worlds must be astronomical, maybe more than 10 in dollars. He initially called the idea schizophrenia with a vengeance.
Yeah, I can see why. It saves the elegance of the Schrödinger equation, but the price is an infinite or near infinite multiverse. That feels like a huge metaphysical leap.
That's the main criticism. If these other worlds are by definition unobservable, how is this scientific? Isn't it just unfalsifiable metaphysics? Everett's own supervisor, John Wheeler, initially supported it but later distanced himself, worried it took physics into a kind of mystical realm.
Yet, Many-Worlds has serious defenders today, right? Especially in fields like quantum computing.
It does. David Deutsch, a pioneer of quantum computing, is a prominent advocate. He argues that the sheer power of quantum computers, their ability to explore exponentially many possibilities simultaneously, is almost inexplicable unless they are literally harnessing the computational resources of vast numbers of parallel universes.
So he sees quantum computation as almost experimental evidence for the multiverse.
That's his claim. It's a bold one and highly debated, but it gives MWI a potential empirical hook, at least indirectly.
Still, even proponents admit there are tricky questions, like the preferred basis problem.
Yes. What exactly constitutes a measurement or interaction that causes the branching? And along which basis or set of properties does the universe split? Why spin up down and not some other quantum property? Defining the branching structure rigorously is still a challenge for MWI. It remains elegant mathematically, but challenging philosophically and empirically. #tag outro. So where does this leave us? After almost a century of debate and these incredibly powerful experiments ruling out local realism, the philosophical battle just keeps going.
It seems like the anti-realist path, Copenhagen, QBism, is kind of passive, isn't it? It gives you a fantastic tool, maybe the best predictive tool ever, but it essentially tells you to give up on asking what's really there.
Right. It focuses on prediction, information, belief. It works, but it potentially sacrifices understanding the underlying mechanism.
Whereas the realist approaches Bohm's pilot waves, physical collapse theories, many worlds, they're active. They're trying hard to paint a picture of reality to make the theory complete.
But each comes with a really heavy price tag. You have to accept spooky non-locality or add new physical laws for a collapse that seem a bit ad hoc, or believe in an unimaginable number of parallel universes. There's no easy realist answer.
It all seems to boil down to that core philosophical question we started with. Do the fundamental concepts of our best theories, like the wave function, actually correspond to real things in the world? Or are they just useful calculation tools?
And in quantum mechanics, maybe more than anywhere else, you can successfully use the whole mathematical machinery to predict experimental outcomes based on past experience without ever committing to what the wave function is. You only need to know how states relate to measurements.
Okay, so wrapping this up, what's the final provocative thought for you, our listener, to chew on? We've talked about all these interpretations fighting over the meaning of the quantum formalism.
But here's something deeper. The current standard quantum mechanics, the framework all these interpretations are trying to make sense of, is itself known to be incomplete in a different way. It's background dependent.
Meaning it assumes a fixed stage of space and time for quantum events to happen on.
Exactly. It needs a pre-existing space-time geometry. But we know from Einstein's general relativity that space-time isn't just a fixed stage. It's dynamic, it curves, it interacts with matter and energy. Gravity is the curvature of space-time. A truly fundamental theory needs to be background independent.
So maybe the deepest quantum mystery isn't the wave particle thing, or the collapse, or even non-locality.
Maybe the biggest puzzle is that we're spending all this effort interpreting a theory whose fundamental description of space and time doesn't mesh with our best theory of gravity. Perhaps the real answer to quantum weirdness will only emerge when we have a unified theory of quantum gravity, where space-time itself is quantized.
Leaving us wondering if our current interpretive debates are happening within a framework we already know isn't the final word.
It's definitely something to keep in mind as the quest continues.